Hello everyone, I am Dr. Rishikesh Bharti. I am an associate professor at the Department of Civil Engineering, and this is the NPTEL's course on remote sensing for natural hazard studies. I am the course instructor of this course. I will just briefly introduce you to the syllabus. So this is a 12-week course with 10 modules, and here you can find the details of all the modules which is in this table. So it starts from basics of remote sensing, then concepts of remote sensing, data processing and so on, and ends with the drought studies. And after each of the modules, you will have an assignment that you need to complete to better understand the concept which is discussed during the classes. Information related to assignment and submission will be available in your NPTEL login. You may also ask your doubts through your NPTEL login, and there will be a few live sessions also during these classes, and that will help you to discuss and clarify some of your doubts. As this course does not have any prerequisite, any level of students and working professionals can register for this course. This course can be taken by BTech, MS, MSR, MSc, MTech and PhD student, as well as the working professionals. So with changing climatic condition and increased anthropogenic activities, natural disasters are very frequent nowadays. This course will introduce you to the geospatial technique as an important tool in studying the natural hazard. This course has two important aspects. First one is remote sensing. The second one is the natural hazard. The basics of remote sensing will be covered in this course, required to understand its application potential. Flood, cryosphere, avalanche, glacial lake hazard, landslide, liquefaction, drought, this kind of hazards will be covered in this particular course. While introducing the application potential of remote sensing in hazard studies, a few case studies which are published in reputed journal will be referred here to explain the concepts and clear the concepts of remote sensing application in hazard studies. So with this we will start this course. Let's begin. So this is module 1, basics of remote sensing, and lecture number 1, introduction to remote sensing. When we talk about remote sensing, we have a few questions in our mind, like what is remote sensing, what do we measure, and then what kind of output we get. So to understand or to clarify these doubts, let us start this basics of remote sensing, and I hope by the end of this lecture you will get all the answers of these three questions. So remote sensing is the art and science of making measurements about an object or the environment without being in physical contact with it. So here there are two important things, that this is a art and science. That means it is not the complete answer of your question or the problem. However, this can be used to gather the information which can be part of your analysis or study that is dedicated to a particular problem. So this is the measurement about an object, and this is without being in physical contact with it. So how do we generate the information without getting in touch with the object? So the media is light, right? And we generate the information in terms of images. So here there are two things, one is object, another is environment. So it is not only the feature that we want to capture, we also want to capture the information, right? So you will be able to understand these concepts. So let us start with very basic. So when we have an object, how our eyes are able to see them? So first the sun illuminates the target, and here you can see the light is falling on this particular object, and then what happens when light falls on this particular object, what happened next? It will get reflected. So when it is getting reflected, our eyes will get that information, will capture those energies, and then our brain recognize the object. This is how we are able to see a particular object or feature in our surrounding, right? So the same thing is being done by the instrument. You can see here in this video, this particular satellite is looking at one particular position, and then continuously it is getting the reflected energy or emitted energy or back scattered energy from the surface, and then it is generating the images. So we are able to see an object when light reflects from it, falls on the retina of our eyes, and the brain recognize the object. This is how the objects are seen. The sensitivity of our eyes is limited to the visible region of the electromagnetic spectrum. So the visible light is from 400 to 700 nanometer, right? As you view the screen of your computer monitor, you are actively engaged in remote sensing. So now also you are doing the remote sensing, but in general, the accepted meaning of the remote sensing refers to the instrument based measurement, right? So we will be using or exploiting the information which is carried by the electromagnetic wavelengths. So let us understand this electromagnetic wavelength. So you can see here this slide, it starts from radio wave to gamma rays, right? And here you might be knowing that gamma rays is having the highest energy, right? So here the energy that you can see here, and the wavelength is very small, and radio wave, here the wavelength is very, very long. So as we move from gamma ray to X-rays, then ultraviolet, then visible, then infrared, then microwave, and then radio wave, the wavelength is increasing. So that means the shortest wavelength that will have the highest energy. So that's why the gamma rays that can give you the information related to nuclei, whereas the X-ray, which is having comparatively lesser energy, that will give you the information related to atom. Then again we are moving further and we are moving to ultraviolet, and here this is related to the molecular level. Then when we use the visible light, we can identify the microbes. When we move to infrared and then microwave, the bigger size objects are seen, you can see here. So the frequency is also given here for gamma rays to radio wave, and the thermal energy. So the thermal energy available at the shorter wavelength will be higher than the radio waves, right? So this information is very, very relevant, and it is very, very important to understand the concepts of remote sensing, how remote sensing is being used in, or how the electromagnetic wavelengths are used in remote sensing. So the electromagnetic waves, wavelength, size comparison, frequency, thermal energy for emission. So that is very, very important. Now in this slide, I am just trying to explain you what are the different wavelengths that we are using in remote sensing. So the first domain is reflective domain. So in the reflective domain, it starts from visible 0.4 micrometer to 0.7 micrometer. Here this is the wavelength where our eyes are sensitive, right? And VNIR and SWIR from 0.7 to 2.5 micrometer. So these two wavelengths are reflective domain, and the reflective domain means the information that you will be getting, it is from the top layer of the surface, because reflection is a property of top layer, right? So from this layer you will get the information when you collect the data in reflective domain. That means a image generated in this wavelength will have the top surface information of the target. Now the second domain, which is thermal domain, where we measure the emitted energy, the emission part. So, this is the information which is coming from the volume of that particular surface. So, this is not the superficial information. Remember, in thermal infrared, we measure the information which is emitted by the target, and emission is a volumetric property. That means this is going beneath the surface, right. Now, the next domain is microwave domain. So, here we measure the back scattering, and the wavelength ranges from 0.1 centimeter to 1 meter, and here the wavelength is long. If you remember the previous slide, the reflective domain, here the wavelengths are comparatively shorter than thermal than microwave. So, this is the longest wavelength we have in remote sensing, and here because of the longer wavelength region, we have some advantage over this emission and reflection that we will discuss in coming slides. Now, in the reflective and emission, these two domains together known as optical remote sensing. Optical remote sensing, and this is known as microwave remote sensing. So, if somebody asks what is optical remote sensing, then you can say that 0.4 micrometer to 16 micrometer, that is the range of optical remote sensing, whereas microwave wavelength ranges from 0.1 to 1 meter. So, it is very important that when we are using this electromagnetic spectrum to exploit or to gather the information about the target, we need to understand how the light interact with the object. So, your source can be anything. It can be a man-made source or it can be sun. So, let us assume this is solar energy which is falling on a particular object. So, this falls on this particular object, and then some amount of energy will be reflected, some amount of energy will be transmitted, some amount of energy will be absorbed by the target, and when it is absorbing, to maintain the equilibrium with the surrounding, some amount of energy will be emitted, right. So, you remember this thermal remote sensing, here we measure the emitted energy. So, I told you this is a volumetric property. Why? Because this volume of the material is absorbing the energy, and this whole volume is responsible for this emitted energy. So, using this information, we can generate this kind of a spectra that we will discuss in coming slides. So, what governs this interaction, what controls this interaction is the internal atomic structure and the composition, right. So, this internal atomic structure and the composition which are responsible for producing this kind of characteristic spectra for a given material. This is for granite. So, these you can see there are few troughs here and there are some peaks, right. So, in remote sensing we are bothered about these troughs. Why these troughs are happening? Because these are the energies which are reflected by the target. So, there is no interest of the target in these wavelengths, but these wavelengths were absorbed, right, that is why it is low. So, if it is absorbed, that means the material composition and the internal atomic structure has something to do with this particular wavelength, right. So, these wavelengths where we get the characteristic absorption feature, these characteristic absorption feature can be considered as the fingerprint of that material that can be used to identify these material in any given satellite image, right. So, here this particular section of this slide explains how the remote sensing is being done. So when sun illuminates the target, so target is our surface. So from surface some amount of energy is getting reflected. So let us consider only 0.7 to 2.5 micrometer wavelength range. Here these energies are getting reflected and it is going and captured by this particular satellite, and this satellite will generate the image, and then whenever this satellite comes in the proximity of this ground station, right, so then this will be transferred to ground station, and then subsequently this will be distributed to different users who are interested in the analysis of these images. So in the previous slide I showed you that light is coming and falling on this particular surface here, and then it is getting reflected and captured by the sensor. But it is not very simple. Why? Because our atmosphere has so many constituents. So we have gases, aerosol, dust particle, clouds, all are playing major role here. So when light is coming from the sun and it is getting into our atmosphere, then it interacts with our cloud, atmosphere, gases or dust particle, aerosol, and then some amount of energy will be diverted from here. So that is known as scattering, right. Some amount of energy will be directly coming to our surface and then they are getting reflected. So now here you see, because of the dust particle or gases, it is getting scattered. So this scattering, after this is coming to our sensor. So this kind of data which is getting captured, it is having the additional information from our atmosphere, right. So this kind of information which is getting into our system, we have additional information from the atmosphere, and this atmosphere is giving you the path radiance. This additional signal which is getting along with the correct signal which is coming from the ground, this is called path radiance. Path radiance, right. So here the light which is coming from the sun, it is known as the irradiance. This is called as the radiance, right. So this is radiance and this is called the path radiance, right. I hope this is clear to you. So we have irradiance coming from the source, that is here, and then it interacts with our atmosphere, gases, aerosol, dust particle, clouds, and then some of the energies are getting scattered, and this scattering will lead to the additional information to your satellite image which is coming from the ground, right. And this is path radiance, this is radiance, this is irradiance. Remember this concept because we will be referring these concepts again and again in future. Now the next domain, which is the emissive domain, remember the thermal remote sensing. So here the thermal emission, it also passes through our atmosphere, right. So the gas or the dust particle or the aerosols, they are also absorbing some amount of energy, and if some material is absorbing the energy, that means it will release the energy at the higher wavelength when they want to maintain the equilibrium with the surrounding. So in such cases you will have the atmospheric emission, that will also be part of your this actual measurement, right. Now the next section is the field data collection. So in the field, what we do in remote sensing, we also have a sensor which is equivalent or similar to the satellite specification. So here we have the field data collection section. So here we have the sensors which are available in these satellites, the similar specification we have, and we try to generate the data in the field and we try to correlate with this satellite images so that we can upscale the information from ground, right. So this is known as upscaling of the ground information to the satellite scale. This will help you to validate your analysis. This will help you to correct your data. There are many applications of the ground based measurement. So now in remote sensing, we refer sun as our source of light, right. So when we have the sun as our source of light, it illuminates the target and then this signal gets reflected and then it is getting captured by the sensor or the receiver, right. So this configuration is known as the passive remote sensing. When we talk about the active remote sensing, you see the sensor itself has a source of energy. So it illuminates the target and then it also measures the reflected, emitted or back scattered energy. So in such situation, we will call it active remote sensing. So active remote sensing, where we have our own source of light or where the sensor has its own source of light. In passive remote sensing, where we rely on the solar energy, right. This is the platform. So in remote sensing, we refer many times the space-borne satellite or airborne measurement. Sometimes you might have heard about the UAVs. So what are they? Whether they are space-borne, whether the satellites are airborne? No. So you need to understand this. Space-borne means which is located in the space, where your sensor is located in the space. So the typical height or the altitude of the satellites are 700 to 900 kilometer. Here you have 185 to 575 kilometer. So this will be referred to as space-borne measurement. When we place our sensor in the air or in the atmosphere, within the proximity of the atmosphere, we call it airborne. So airborne data acquisition refers to aerial photography, airborne SAR, aerial television, that is also a airborne proximity, then UAV. So all these are airborne data acquisition. So you have two major categories, space-borne data acquisition and the airborne data acquisition. So if you remember the questions that I mentioned in the first slide, that what is remote sensing, what kind of information we gather, what kind of output we get, right. So this slide has a photograph. It can be captured by our normal camera, it can be captured by a DSLR, it can be captured by our mobile phones, right. So this kind of images we generate. This image is again taken by the mobile camera or the DSLR. Here this is also a DSLR and this image is also from DSLR. Now this kind of information can we generate with our normal mobile phone or the DSLR or any other camera? This kind of information. So what is the difference between all these images? So the distance between the object and the data acquisition system. So as you go far from the data acquisition system, what happens? You will cover the larger aerial coverage, right. You will have better aerial coverage. So that is what I meant here. So here you have two different modes of data acquisition. One is your mobile phone, another one is your satellite, right. So what information you are getting in satellite images, what information you will get in the mobile phone images. So this is very different from your mobile data or from your normal DSLR or any other camera, right. So that we will try to understand. So when we talk about the digital image, because these images are digital image. So these are produced by electro-optical sensors. It cannot be sketched, it cannot be scanned, right. So, we are generating this kind of images by electro-optical sensor, and these electro-optical sensors output, that means this digital image, it is composed of tiny equal areas or picture elements abbreviated as pixels. So, in general you will be calling them, or a remote sensing community calls them, pixel. So, here you are not able to see any pixel, right? But when you zoom at your screen, you might have observed that after a level your images will get pixelate, right? So, when you see the square boxes, these are basically your pixels. So, these pixels are nothing but the energy which is captured by your detectors, and it is arranged in a regular manner, and then you are able to see this kind of images. So, with each pixel a value is associated known as digital number, brightness value or gray labels. So, any of these can be used to call the values which is associated with the pixel, which is an record of variation in the radiant energy in discrete form. Right. So, before I move further, I want to explain one concept which is called, suppose this is a spacecraft, right. So, spacecraft is a carrier, and in these spacecraft you have many sensors attached, and each of them have different specification. So, let us say this is the sensor, and this sensor is having the detectors arranged in a manner so that they will be looking at the ground, and each detector has a field of view, right. So, this field of view will be responsible, and the height, the altitude of this sensor, that will define how much area it will cover on the ground, isn't it? So, if let us say this is looking at 1 by 1 kilometer, and this height is 100 kilometer, you can easily find out what is the field of view, right, or the field of view is given and this is given, you can find out the altitude. So, this is very easy. So, the basic physics and maths will be referring, and here you can see all these pixels are generated. So, these individual detectors are responsible for generating this one pixel, right, and this one pixel will have the information which is reflected, emitted or back scattered from the surface, and they are known as the digital number, right. I hope this is clear. So, the digital numbers are the associated values with the pixel which is generated by the detectors available in those sensors, right. So, once we have this image, because the output generally what we get is the image, right. The output of the sensors, that are the digital images. So, when we see the image, we zoom it and we try to see the pixel, but we can't see the numbers here, which is the digital number, right. So, what we do is we just simply try to import this in any programming language, and you will be able to see this kind of matrix, and these matrix value the element of this matrix. This is the reflected, emitted or back scattered energy from the surface. So, this kind of information we are generating from the remote sensing. So, from remote sensing we are generating images as well as the data. It is not necessary that always we will have the images, right. We can also have the values. It cannot be in the form of, or it may or may not be in the form of image. So, that is very important to remember. Now, once we have this image and we have imported this information into any programming language, so what shall we do with it, right? So we need to understand how the light is interacting, how the material is behaving. So an object reflecting more energy records a higher number for itself on the digital image and vice versa. That means within the field of view, if you remember the field of view of a detector, within a field of view, if the value is high, that means you are having the brighter object comparatively, and if you are having the darker object, that means you are having the dark color material in your field of view, or the chemical composition which is eating all the energies, that is responsible of giving you the high and low numbers in the form of digital number. So here you can see this is one image that we are trying to generate, right. In this slide I want to explain this dark and bright object concept. So here you see this particular satellite is looking at this particular section of the ground, and here we have one bright and one dark object. So definitely the reflected energy which is reaching to this particular surface will have different numbers, because what happens, this particular energy will be higher than this dark object energy, right. So this will be very clear in your digital number. So when you will see the matrix, you will find the value corresponding to this particular object will be higher than this, right. Once we have the image matrix which is imported in any programming language, then you can also draw the histogram. What is a histogram? What is its uses in remote sensing? So this is the basic analysis of the remote sensing data. Here what we do is we try to identify all the unique values from this particular matrix. We put them into x-axis, right, and in the y-axis we will identify their frequency, and then we will try to plot this kind of histogram. This will tell you whether the value, let us say this is 255, right. So within the given range of the unique value, how the frequency is distributed, whether your histogram is like this, skewed in the left side of the histogram, or whether it is skewed at the right side of the histogram, or whether it is having a Gaussian distribution, right. So if you have this kind of histogram which is skewed towards the lower value, right, this is, remember, 0 to 255. Let me write this for all the axes. (255). So if your image histogram is skewed towards the left side, that means towards the lower value, right. So then it indicates your image will be dark, right. Here it is skewed towards the right side. So that means this image will be bright. And if you have a Gaussian distribution, that means your image is having the appropriate contrast and brightness, right. So this is very good for the image, but in general, since we are measuring in the natural condition, natural objects, we generally get this kind of histogram for our image, which needs the further digital image enhancement, right. So when we talk about the data acquisition, here you see this particular satellite. So satellite, remember, is a carrier, right, and this carrier is having so many sensors, and here one of them is given here, right. So one of them is attached here, which is looking at the ground, and this particular sensor is having this kind of arrangement, right. So here this is the detectors, and all the detectors having the field of view, and one of them is responsible of generating this particular pixel, right, and this is getting captured and this is getting arranged in the form of image. So, the one detector is responsible of generating this pixel, next detector will be generating this pixel, the next detector will generate this, next left side this, like this we will complete the image and we will have all the pixels, right. Now, the energy which is released or reflected from this particular portion of the area reaches to this particular detector, and here we have analog to digital converter, ADC, and the depending upon the ADC whether it is 2 bit, 6 bit, 8 bit or 10 bit, 12 bit, your image will have the digital number. So, this is the signal that is getting converted to digital number with the help of analog to digital converter, and this is generating your digital number, right, and this is getting stored in this particular image, right. So, here you can see this one pixel you can consider, and then this one pixel will have the digital number converted by the ADC, right. I hope this is clear, and the background of this image is your image matrix. So, these elements are nothing but the digital number reflected emitted values captured by your sensor, right. So, now you can understand how remote sensing images are different from our normal camera image, because in remote sensing it is essentially a instrument based measurement where we have a option to select the appropriate detectors which are sensitive in a particular wavelength range. But in mobile phone what happens, we generally use the 400 to 700 or 400 to 1000 nanometer, right. In remote sensing we utilize the visible as well as the other wavelengths also, whereas in mobile phone we use only the visible and the beginning of the infrared, right. So, this is the major difference. So, here you will have the information which is captured in the thermal, in the microwave domain, which is not possible with our eyes or with our mobile phone or the regular mobile phone, right. So, with the help of remote sensing instrument, we can generate several images in different wavelength for the same area at a time, right, which is not possible with our mobile phone, because when we capture the image with our mobile phone, we get only one output and it has the RGB combination, right. But when we talk about the remote sensing satellite, so this satellite, this is basically a carrier, and then here you have one detector. This detector is nothing but the bundle of detectors, and each of them are responsible for generating the pixel information, and each detector is having a specific field of view, and they are looking at the ground and they are having the footprint, right. So, this detector we can have one detector in the wave in the range of 400 to 500 nanometer. Another set of detector in the same sensor we can have that is sensitive in 500 to 600 nanometer, right. So, likewise you will have one image from this 400 to 500, then 500 to 600, then 600 to 700, 700 to 800 nanometer. Like that you will have 1, 2, 3, 4, and this can be extended till microwave, right. So, this kind of information which is available to us, which cannot be generated with our regular camera, that you need to clear. So, for example, this is one image which is generated with blue wavelength, then another image generated with green wavelength, this is another with red wavelength, then this is NIR wavelength and SWIR wavelength. So, you can see here with the same sensor we are able to generate 5 different images, which is not possible with the normal or regular camera, right. So, here if we consider one of the pixel here which is highlighted here, so we will have, because we are looking at the same ground and this all these images are captured at the same time, right. So, if we consider this pixel is basically here, this pixel is basically here, here, here. So, if we consider this particular setting, then we will have 1, 2, 3, 4, 5 values for that particular pixel. That means the 5 pixel means the wavelength we have 400 to 500, then 600, then 700, then 800, 900, right. So, let us say one first image, this image is giving you this particular point for that particular material, right. For the same pixel in this green wavelength we have values here, for the red wavelength we have one value here, for the next NIR band we have one value here, for the SWIR we have one value here. So, if we connect them, we will have the information related to this particular material, how it is behaving with respect to wavelength, right. So, this kind of information you can generate, which is not possible with the normal camera, right. So, here we try to gather the information how a material is behaving across the wavelength, and remember the property or the absorption feature which is generated by these material is representing their chemical composition and the internal atomic structure. So, ultimately we will be able to produce this kind of a spectra, and these characteristic absorption feature we will try to study and we will try to identify, and then we will say this is granite, right. So, this is the basis of remote sensing, how remote sensing is been done for natural and man-made material. So, these characteristic absorption feature is a fingerprint of the material. So, one individual absorption feature or set of absorption feature can be considered to identify the materials in remote sensing images. So, to understand the remote sensing, you need to understand the resolution, because this will help you to identify appropriate images or the satellite or the sensor, which will help you to gather the information which is required in your study. So, the first one is the temporal resolution, the second is radiometric, third one is spectral, and the last one is the spatial resolution. So, we will see them one by one and we will try to understand how these are used, these concepts will be used to identify appropriate sensor satellite for your study. So, the temporal resolution, this depends on the return time of the satellite, because if you remember that this is our earth and the satellite is moving in a fixed path, right. So, this is called orbit. So, these orbits are fixed. So, if the altitude of this sensor is let us say 1000 kilometer and there is another one which is 2000 or maybe 1800 kilometer. So, definitely this 1000 kilometer satellite which is moving at this particular path will take less time to cover this will take more time to cover this. So, this is important to know what is the return time of your satellite to capture your study area, right. So, return time is a function of altitude at which the satellite is launched. Higher the altitude, more circumference of the orbit and longer to orbit the earth. With the ability to tilt the camera system, revisit capability can be increased. So, suppose if this is the, let us say I will draw the ground, this is one sensor, right. So, this is one sensor which is looking at this particular ground. Now, in the next, because earth is also moving in its axis and the satellite is also moving along its orbit. So, what happens at a particular time, it will be looking at this particular area, right. So, here your image will be generated, but this for this location it has to come again, and then when the orbit is matching with this, then only this area will be covered. But if we can tilt this camera from here itself, we can capture this area, right. So, this is the meaning of this. With the ability to tilt the camera, revisit capability can be increased. I hope this is clear. So, the ability of tilting the camera or the satellite sensor, that will help you to gather information of your surface, maybe before it the orbit matches with your study area. So, this is one example. So, this image is captured in January, in February, in March, in April, in May, and then 25th at the end of the May. So, here what is the difference? So, as of now, please consider this red color representing vegetation. So, this red color, here you have dark red, here you have bright red, then slowly this is getting changed into this. That means, if I consider red color as vegetation, the vegetation is changing, vegetation has been removed. So, we can't say that this is a forest area, because from January to May everything got converted to cyan color, right. So, this is a agriculture land, and here this can be the young stage, and slowly it gets harvested by this. So, this indicate that this particular area people have used to cultivate some of the crops, and then subsequently they got harvested in 25th May. So, this kind of temporal information will help you to gather the information. This is another example where you can see the white color, these are basically the clouds. So, how the clouds are moving. So, morning 5:30, 8:30, 11:30 and the evening 4 o'clock. So, with this you will be able to forecast the weather condition. This is how the weather forecasting is being done. So, where remote sensing images are one of the primary input, right. This is another example of temporal resolution. Here you can see that 1992 and 1988 both are represented with two different colors. So, in 1988 this river boundary was here, the yellow color. In 1992 it has been changed to this orange color. Then again with respect to 1988, this 2002, how river is changing its course. So, this temporal images which is captured at different time frame by the same sensor, that will help you to gather the information how things have evolved, how things are changing. This can be done for a forest area, how the area is increasing or decreasing for a given forest, how a river is changing its course, how a particular campus or how a particular building is evolving with time. So, we try to capture the images time to time, and then we will gather this information and we will use them into the modeling. Next concept is spatial resolution. In very general way, I will explain you this spatial resolution. So, you have generated an image and the image is nothing but the linear arrangement of the pixels, right. So, these pixels have the value which is called digital number, right. But this area which is captured or which is representing the ground, we need to have the number. So, whether it is for the 15 by 15 meter or whether it is for 1 by 1 meter or whether it is 1 kilometer by 1 kilometer, right. So, this is known as the spatial resolution. If you have better spatial resolution, that means you have smaller size representing the pixel, right. So, it is a measure of the smallest angular or linear separation between two objects that can be resolved by the sensor. Here you can see this particular image, the one pixel is 23 meter by 23 meter. That means this pixel representing the 23 by 23 meter ground surface. Another image, here you have 2.5 by 2.5 meter. This is 0.5 by 0.5 meter. So, definitely when we are having the smaller area, that means the images will have more information, right. So, this is another example. So, when we are having the lower resolution or the coarse resolution, so in spatial resolution we refer fine and coarse and medium resolution. The coarse resolution means the bigger the pixel size. The bigger the pixel size means let us say 1 kilometer by 1 kilometer. Medium resolution, that means 30 meter or 23 meter, these are the medium resolution. When we refer to 2.5 or 0.5 meter, they are having the fine resolution. So, nowadays we have the spatial resolution in terms of centimeters. So, there are some sensors which are able to produce the images in centimeter level. So, those have better information about the surface area, right. So, I hope this spatial resolution is clear. Now, the concept of IFOV and FOV, spatial resolution is the projection of the detector element on the ground through optics, right. So, here if you remember this diagram, this one detector is looking at this particular area on the ground, right. So, here the size of the pixel is basically your spatial resolution. So, one detector is responsible for generating one pixel information and this is known as IFOV, instantaneous field of view, and this is the field of view for the entire sensor. This is combination of all these detector, right. So, IFOV specifies the sensor as independent of the altitude, because does not matter whether it is airborne or spaceborne data acquisition, this IFOV will remain same, right. So, it is independent of the altitude. Now, comes to the radiometric resolution. So, the radiometric resolution, in the simple word you can understand that the amount of energy which is coming from the surface, in how many labels we can differentiate it, how many subtle changes we can identify in the incoming radiation. So, it defines the sensitivity of a detector to differentiate in signal strength as it records the radiant flux reflected or emitted from the object. So, if remember the ADC I mentioned, analog to digital converter. So, if the ADC is of 1 bit, so 1 bit means 2 to the power 1. So, is equal to 2, right. So, 2 means you will have only 0 and 1 value, right. So, either your sensor will identify the signal or it will not identify the signal, right. So, for the darker material it will be 0, for brighter it will be 1, but more than that you will have no information. So, here this is 1 bit. When we increase the radiometric resolution of our sensor, this is 2-bit. When we use 2-bit, that means we can differentiate the incoming radiation into 4 groups or 4 classes. When you further increase this to 3-bit, then 4-bit, you can see how the same area is appearing. So, when we are increasing the radiometric resolution, definitely we will have the better information about the target. This is one example. Here you have 3-bit, here you have 8-bit, right. So, the same area, you can see how much information is available in 8-bit, how much information is available in 3-bit. Now comes the spectral resolution. It refers to the number and dimension of specific wavelength interval in the electromagnetic spectrum to which a sensor is sensitive, right. So, when we explain the spectral resolution, we try to explain few concepts here. First one is, let us consider this is 400 nanometer to 2500 nanometer. This is the wavelength range. Now, I have a set of detector, that means I have a sensor which has different detector sets that is responsible of generating one image using this particular wavelength. One is this, another one is this. So, within a given wavelength, how many images that we are generating, that comes under the spectral resolution. But there are few more concepts that you need to understand, and then we will talk about the spectral resolution. So, first is within a given wavelength, how many images we are generating. So, here let us consider we are generating 3 images. Now, each of the images will have a beginning and end of the wavelength. So, let us say this is first image is from 450 to 550, right. Second image 575 to 675. Third image maybe 700 to 800 nanometer, right. So, when we have this, we can explain what is the beginning and end of this particular images, that is first thing. Second thing is how many numbers that my sensor is generating, that is second thing. So, it refers to number and dimension of the specific wavelength intervals in the electromagnetic spectrum to which a sensor is sensitive. So, the first one is this whole wavelength. So, I will write 450 to 800 nanometer, that is my first information about the spectral resolution. Then second is 3 images that we are generating, right, and the third information will be their starting and end wavelength, right. So, if we have all these together, it is known as the spectral resolution, right. So, you see here this left hand of this slide, here you have 5 bands. So, when we have 5 bands, that means for a given pixel we can have the 5 values, if you remember the previous concepts. So, for this particular pixel you have 1, another from this image, from this image, from this image, from this image, and that we are using to generate this kind of spectral profile, right. When we have 200, 400 or 500 or thousands of images generated at the same time by the same sensor, we will have thousands of points to plot here. So, for this we can call it low spectral resolution, for this we will call it high spectral resolution. So what is the benefit when we are having the high spectral resolution? Because if you remember, the light interacts with the matter and the characteristic absorption features are produced by the chemical composition and the internal atomic structure. So when we have this, that means these absorption features are missing when we are having the low spectral resolution, because we do not have the information between this and this point. But here between these 2 points we have so many points, right. So when we are having the spectral resolution high, that means we will have more information in different wavelengths, whereas in the low spectral resolution we will have limited information and the in between information, whether it is supposed to be a absorption feature or whether it is a reflectance curve or reflected energy, it is missing, that is unknown to us. So it is always better to have the high spectral resolution when we are trying to identify the material property and composition. So a spectral band is defined in terms of the central wavelength and the bandwidth. So here you can see in this particular image. So this is the sensitivity of that detector. So let us say this is starting from lambda 1 and this is lambda 2. So that particular detector sensitive to a particular wavelength, we say that it is 400 to 500 nanometer. Let us assume this is 400 and this is 500, right. But actually when we see the sensitivity of this detector, we find that it is not having this kind of sensitivity, right. It is having the Gaussian distribution. The Gaussian distribution means at a mean level it will have the maximum sensitivity. So actually if you see, this is the wavelength range where this detector is actually gathering the information and which is the true representation of the target, right. And these wavelengths will have very small information about the target, right. Full width at half maxima is used to characterize our detector, its sensitive wavelength in which they are generating the image. So here the central wavelength, which is the central wavelength of this particular detector, the sensitivity, the bandwidth, it will be 400 to 500, and the FWHM, that may be that 425 to 475, right. So this is the actual wavelength where this detector is sensitive. Selection of bandwidth is a trade-off between the energy to be collected and the spectral shape of the feature to be observed, right. So when we decide which kind of detector we should use in our sensor, it is based on what is the mission or the target or objective of this particular sensor development. So when we are having more or the high spectral resolution, we get this kind of spectral feature, right. So where we can identify the minor changes in the composition, which is not possible with the multispectral data, right. Now I will try to explain you panchromatic, multispectral and hyperspectral. This multispectral image is one band image and it is using a broader wavelength range of the electromagnetic spectrum. So let us say it is using 400 to 1500 nanometer. This whole range is used to generate only one image. So in this slide I will try to explain this panchromatic, multispectral and hyperspectral remote sensing. When we talk about the panchromatic images, so we are using a broader wavelength range starting from let us say 400 to 2500 nanometer, or I will make it 1500 nanometer, and this whole range is used by the detector to generate one single image, right. So, one single image, that is this one. So, what happens? I told you in the beginning the relationship between the wavelength and energy. When we are using the shorter wavelength, we are having the high energy. That means the spatial resolution. If you remember that your sensor is here and it is generating one pixel here, and if the wavelength is the shorter wavelength, this one, that means it will have high energy, and this has to travel through our atmosphere to space to get captured and the image will be generated, right. But when we move to the longer wavelength further here, the energy will not be sufficient to travel, right. So, what we do is we try to increase the ground or the pixel size, because here in the shorter wavelength we had high energy. So, smaller area is able to produce the sufficient energy that can travel to reach to this sensor. When we talk about the longer wavelength region, the energy is comparatively less, so that we have to increase the area, and that area will be able to produce the reflected energy or emitted energy that will travel through our atmosphere to the space, right. So, that is the difference between the panchromatic and other type, because in panchromatic we are using the shorter wavelength region, and because of the shorter wavelength region we have high energy, and the smaller portion of the ground can produce the sufficient amount of reflected or emitted energy that can travel through our atmosphere to the space, and that is able to get captured here. So, when we are having the smaller size representation on the ground, that means you will be able to see more information on your image, right. So, that is panchromatic. So, panchromatic is one image, right. Now, the next one is multispectral. So, remember in panchromatic we use the entire wavelength to generate one image, but in the same wavelength, let us say 400 to 1500 nanometer, we can have different configurations of detector which is able to produce, let us say 4 images, right. So, these 4 images will be different, because here we are having very specific wavelength range. That means in the ground again we have to increase the spatial resolution, then only it will be able to travel and captured by the sensor. So, here you will have relatively coarser spatial resolution compared to your panchromatic, and here the number will be more than 3 or the minimum 3, right. So, that is called multispectral, and the wavelength gap, there can be a gap between 2 bands. So, these wavelengths there can be a gap, right. So, this is first, this is second, this is third, this is fourth, right. Then you have hyperspectral. So, in hyperspectral, in the same wavelength region, what is happening? We will generate so many of images without having any gap, right. So, here you will have many images generated in the same wavelength region, but there will be no gap between them, and the number of the bands, the number of bands means I am referring to number of images, right. So, number of bands will be more than 10, right, and these will be not continuous, it is contiguous. Contiguous means there is no gap between the first and second band in the wavelength, right. So, this is called contiguous in nature, and it will have very narrow bandwidth. So, the bandwidth we discussed in the spectral resolution. So, this is the bandwidth, So, starting and end of the wavelength. So, typically in the hyperspectral remote sensing we have 10 to 20 nanometer bandwidth, and it is contiguous in nature, and the number of bands should be more than 10. So, that is hyperspectral. So, if you compare panchromatic, multispectral and hyperspectral, panchromatic will have better spatial resolution, hyperspectral will have more spectral resolution. So, if you want to identify the material, you have to use the hyperspectral. If you want to identify just the material, not the composition, multispectral is better. If you want to identify detailed information about how many trees are there, how many houses are there, how many cars are located in one street, so in such situation panchromatic images will be better. So, all of these are having different application. Slowly we will get into the application, but before that we have to clear the basics. So, here you can see that now the sensor technology. So, how do we generate the images? So, there are different ways of generating the images. The first one is Whisk-broom imaging sensor. So, scanning is performed by an oscillating mirror deflecting upwelling radiation from earth onto wavelength sensitive photodetectors. So, I hope this video will help you to understand what I mean by Whisk-broom. It is like how we sweep our floor, right? So, this is Whisk-broom. When we talk about the another technology which is push-broom, I have another video, so maybe you will see that. So, sensor consists of a linear array of detector equal in number to the number of pixels in a row of the image, more stable compared to Whisk-broom, because here there is no oscillating mirror, and this is frame scanning. So, in the frame scanning you see the whole frame means the number of detectors will be equal to the number of pixels in your image, right. Now, we will also see some of the advantage of remote sensing. So, the image generated beyond the visible spectrum, that means our eyes are sensitive from 400 to 700 nanometer, but with the instrument we are able to generate the images in the thermal as well as in the microwave domain, right. Larger aerial coverage, that will help you to study, identify the morphology of the river, what is the shape of a lake, what is the distribution of the urban area. So, those kind of information is available with the larger aerial coverage. Then temporal images will help you to see the changes, how things are happening. So, here one of the example, how the glacier is moving from one place to another place. Then access to inaccessible areas, that for the military purpose, for the defense purpose, we have also used the remote sensing data set. Now, the last one, which is a very big area, which is called planetary exploration, because remote sensing is the only way we can identify or gather the information about the other planets. So, that we are actively doing. You might have heard about Chandrayaan, Mangalyaan. So, we are continuously sending our satellites to gather the information, and then we will try to analyze them, and then we are identifying the material property or the characteristic of that particular planet. So, with this, thank you for listening me, and we will continue this course. Thank you.